Everybody, this is my video solution for 2019 E&M Free Response Question 1. So, let's read it together. The circuit represented above is composed of the three resistors with the resistances shown, a battery of voltage V0, a capacitor of capacitance C, and a switch S. The switch is closed, and after a long time, the circuit reaches steady-state conditions. After the following questions in terms of V0, R, C, and fundamental constants as appropriate. So after a long time, this capacitor has been charging, taking on all the charge that it possibly will take. And eventually the charges stop moving. Steady state means that these charges are in equilibrium. No more charges want to go onto the capacitor. And nothing is flowing here. That's an important thing to know about the steady state, that nothing is going on in this branch with the capacitor. It shuts off all the current going towards it. So, but there is still a way for the charges to get from the positive to the negative terminal of the battery, and it's through this loop right here. And in this loop, I can see that the charges are going this way from the battery. And one thing I know about any loop is that the sum of the volts in that loop have to be 0. Last year you might have solved this problem. Actually, I'll do this in two ways. We got time. It's distance learning. So I'll do this the loop way. I'll say that, you know what, you get plus V0 from the battery, and you get minus 2Ri across that resistor. What that is Ohm's law. The voltage drop, delta V, across that resistor is I times R. And whatever the current in here, I, that I'm looking for, it's going to drop I times 2R. Minus another R times I, meaning that resistance times I. That's all going to equal 0. Or I could say the V0 equals 3Ri, or I equals V0 over 3R. Other ways, people would probably solve that. If this was AP Physics 1 or like first year physics, I would probably do that problem by saying, look, those are a series. And I would simplify that problem down to a V0, and I'd say combine that into a resistance 3R. Then you'd say, well, the voltage drop across that is V0, and then I equals V0 over 3R. Definitely a simpler way, and looks like an easier way. The problem is that doesn't work for everything. Not all circuits are either series or parallel, so sometimes you can't combine them that way. But there are problems, every problem will work with the loop rule, that you can solve that, and Ohm's law, that'll always be true. So we'll talk more about loops in tomorrow's lesson, but this one just is a few different ways to get A. So, recap, the circuit stops, the current stops moving through that capacitor because it's fully charged, as charged as it's going to be. B, how much charge is on that capacitor? Well, one thing I know is that a capacitor is a charge over a potential difference, or I could rearrange that to say Q equals delta V times C. And that's great, because I know the capacitance is C. The question is, what is that delta V? Well, in this loop, or in this circuit, this capacitor, this branch is in parallel with this branch. So that means the same potential difference that drops here is also dropped here. But I know after a long time there's no current going through this resistor, so there is no potential difference across this resistor. So all the potential difference in this branch is caused by that capacitor, because there's no current, so nothing. This branch, how much potential difference is there? Well, that's easy. That's Ohm's law. Delta V equals I times R. And we know what the current is already. V0 over 3R multiplied by R equals V0 over 3. And that makes sense. A third of the potential difference dropped in this circuit should happen across a third of the resistance. R is a third of the resistor. So the capacitor, coming back down here, has a capacitance of V naught over, has a potential difference of V naught over 3 multiplied by the capacitance of that capacitor. So Q equals C V naught over 3. It's not V naught, it's not equal to the full potential difference of the battery, because in your steady state, you're still getting current moving through here, and you get a drop across here. And if I choose this outer loop as my loop and say the sum of the volts has to equal 0, I go plus V naught minus I times 2R minus Q over C equals 0. That's another way to solve that one, that you can look at that loop and say, okay, I know I is V naught, and this is V naught over 3R times 2R minus Q over C. And solving that out gives us that Q equals C V naught over 3. Just a different way to end up with the same result. And then C, how much energy is stored in the capacitor? No problem at all. The potential energy of a capacitor is 1/2 Q delta V. And Q we already know is C V naught over 3. And delta V we already know, which is V naught over 3. So that ends up being C times V naught squared over 3 times 3 times 2, which is 18. And then I'm sure if you use the other ways to find the potential energy of a capacitor, C 1/2 C delta V squared, or Q squared over 2C, those would work as well. You'd always end up with that same answer. So that's that one. I'm going to save parts D, E, and F for a second part of the problem, which I'll post right now. Come on back for that one.